Actually, today we are going to discuss one particular theorem which is very popular, very important, mostly in real analysis. But we are going to discuss that one in the context of a sequence of random variables. We all know that Taylor series expansion is a very important result or theorem. Actually, this is integrated with math in every branch, almost every branch of mathematics, although it comes from real analysis or calculus. So today we first revisit or just have a quick look on the concept of order in probability, and using the several theorems in that area in terms of orders like big O and small o, or order in probability, we will try to develop this Taylor's expansion in probability for a sequence of univariate random variables. And naturally, what we can do for a sequence of univariate random variables, probably we should be able to do the same kind of thing in case of multivariate random vectors. And this is exactly what we are going to do after defining or after developing Taylor's expansion for a sequence of univariate random variables, and then we will move on to defining or developing Taylor's expansion in case of a function of multivariate random vectors. Here first we will do a quick recap of some of the results related to order in probability, and then we will state and prove or we will discuss how to do Taylor's expansion in probability, and then obviously how to extend this Taylor expansion for multivariate case. So let us first consider an infinite sequence of real numbers as an, and another sequence of real numbers which are positive real numbers, that is Gn. We define an is of smaller order than Gn and write an equals to small o Gn if limit n tends to infinity, an by Gn equals to 0. Another definition relating to the same kind of order in probability, we can define an is a sequence of real numbers. An is almost of order Gn, and write an equals to big O of Gn if there exists a real number capital M greater than 0, such that modulus of n by Gn is less than equals to capital M for all n greater than equals to n naught. Next we will discuss or recap few results on these orders based on real sequences. So let us assume that an and bn are two real sequences, and fn and gn are also real sequences, but for positive numbers, positive real sequences. Then if an equals to small o of fn and bn equals to small o of gn, we have an bn equals to small o of fn gn. Modulus of an to the power r equals to small o of fn to the power r for r greater than 0, and an plus bn equals to small o of maximum of fn gn. The same type of results based on big O we can state as, if an equals to big O of fn and bn equals to big O of gn, then an bn equals to big O of fn gn, an to the power r equals to big O of fn to the power r for r greater than 0, and an plus bn equals to big O of maximum fn gn. And the next result is basically, so one series of results is based on small o, and another series of results is based on big O. So the next result is related to both small o as well as big O. If an equals to small o of fn and bn equals to big O of gn, then an into bn equals to small o of fn gn. Exactly similarly, if we recall the definition of order in probability, we have similar type of results based on the sequence of random variables. Let us state formally these results as let xn and yn be sequences of random variables, and Fn and Gn be sequences of positive real numbers, if Xn, capital Xn equals to small o p of Fn and capital Yn equals to small o p of Gn, here we have to introduce order in probability because Xn and Yn are sequences of random variables. So, under these conditions we have Xn Yn equals to be small o of p of Fn Gn, modulus of Xn to the power r equals to small o p Fn to the power r for r greater than 0, and Xn plus Yn equals to small o p of maximum of Fn Gn. The same kind of results we can state for BGO of order p. Let Xn Yn be sequences of random variables and Fn and Gn be sequences of positive real numbers. If Xn equals to BGO of Fn in probability and Yn equals to BGO p of Gn, then Xn Yn equals to BGO p of Fn Gn, modulus of Xn to the power r equals to BGO p of Fn to the power r for r greater than 0, and Xn plus Yn equals to BGO p of maximum of Fn Gn. Basically, the same kind of results still hold. It does not really matter whether you use BGO or small o. And again, another result we can state which involves both small o and BGO, as if Xn equals to small o p of Fn and Yn equals to BGO p of Gn, then Xn Yn equals to small o p of Fn Gn. We have already discussed the proofs, and the proofs are very simple using simple probabilistic arguments. We are not going into that details right now. Let us consider a few important results, and the proofs of these results involve these orders in probability. First result states that if Xn is a sequence of random variables and An is a sequence of positive real numbers such that expectation of Xn square equals to BGO of An square, then capital Xn equals to BGO p of Fn. The proof is very simple, but we will do this proof, we will prove it technically and in every detail. Since expectation of Xn square equals to BGO of An square, then by the definition there exists a real number capital M1 greater than 0 such that expectation of Xn square less than equals to capital M1 square into An square for all n greater than capital M naught. Now, if we apply Chebyshev's inequality and we choose a particular value of M2, we have probability modulus of Xn greater than equals to M2 An. Direct application of Chebyshev's inequality says that this probability is less than equals to expectation of Xn square divided by M2 square into An square. Now, if we choose M2 to be greater than M1 into epsilon to the power minus half, we immediately see that this quantity expectation of Xn square by M2 square into An square is strictly less than expectation of Xn square by M1 square epsilon to the power minus 1 An square, which is definitely less than equals to epsilon, because expectation of X1 square is less than equals to M1 square into An square, and this holds wherever small n greater than equals to capital N naught. So, what we get is that probability modulus of Xn greater than equals to M2 An is less than equals to epsilon, which immediately implies that capital Xn equals to BGO p of An. The second result is a similar kind, which involves the variance of a sequence of random variables. So, let us state this formally. Suppose Xn is a sequence of random variables that satisfies sigma n square equals to expectation of Xn minus expectation of Xn whole square, which is equals to BGO of An square, and expectation of Xn equals to BGO of An. Then show that Xn, the sequence of random variables itself, equals to big O P of a n. The proof is really simple. We know that if un equals to big O of fn and vn equals to big O of gn, even vn are sequence of real numbers, then un plus vn equals to big O of maximum of fn gn. Now this is true for sequence of real numbers. Now therefore expectation of xn square equals to sigma n square plus expectation of xn whole square. So naturally this is equals to big O of an square from the given condition of the results. So naturally just application of the previous result, that is result 1, we get immediately xn equals to big O P of an, that means big O of n in probability. So now we have some idea about how to do this kind of proofs when some results that involve order in probability, or some of the results using order in probability we can easily prove them. Now we will move on to a very important result that is called Taylor expansion in probability. We all know the Taylor series expansion in case of real variable, but here we will consider this, or we will see whether we can develop a Taylor expansion in probability. First assume that g is a continuous function and this is continuous at x equals to a, and capital Xn equals to small a plus small o p of 1. Then it is easy to show that gxn equals to ga plus op1. Now just remember one small thing, that from real analysis we know that Taylor expansion of a function which has derivatives. That means this Taylor expansion involves the derivatives of the function for which we are considering Taylor expansion. The question is, can we combine these two facts? Like the way we know or we develop Taylor's expansion for a function having derivatives and this order in probability and the continuity, all these things. So combining these two facts means that if we can strengthen our assumption on G to include the derivatives up to a certain order, then is it possible to derive probabilistic analogies of Taylor's expansion? So that is precisely the question. So remember, along with the continuity of the function G, we have to assume the existence of derivatives at least up to a certain order. Then we can think of deriving the probabilistic analogies of Taylor's expansion, and fortunately the answer is yes, we can do that. So now we are going to formally state Taylor's expansion as a result. Let us assume that we have a sequence of random variables which we call xn, such that capital Xn equals to a plus big O P of Rn, and Rn is a sequence of positive numbers that goes to 0 as n goes to infinity. If g is a function with s derivatives, that means derivatives up to order s at a, then g of xn equals to summation j equals to 0 to s jth derivative of g at a, that means g upper bracket j a, into xn minus a whole to the power j divided by j factorial plus small o p of Rn to the power s, where as I just mentioned that g upper j within bracket is the jth derivative of g and g0 equals to g. To prove this result, first consider a particular function which we call hx, which is nothing but gx minus summation j equals to 0 to s g upper j a into x minus a to the power j by j factorial into 1 by x minus a to the power s, if x not equals to a and this is equals to 0, that means x takes the value 0 if x equals to a. Now it is clear that g is continuous at a, and we know that Rn is a sequence of positive real numbers that goes to 0 as n goes to infinity. Then naturally we have h of xn, that is a sequence of real numbers, h of xn equals to ha plus small o p of 1. Hence by the lemma 3 we know that capital Xn minus a to the power s into hxn equals to small o p to the power rn, small o p of rn to the power s, which implies, because if we multiply both sides of h function by xn minus a whole to the power s, we will immediately get gx minus summation j equals to 0 to s g upward j, that is jth derivative of g at a into x minus a to the power j by j factorial equals to small o p of rn to the power s, which proves actually the Taylor's expansion. So, proof is extremely easy, just application of the previous results that we already have proved using ordered improbabilities small o and big O, and this choice of this h function actually does the entire job. So, this is little tricky, little technical, but it is easy to remember this kind of technique which we can use many times in future in several other statistical analysis or theoretical development. So, next we will discuss how to extend Taylor expansion in probability for the multivariate case, and we state this thing as a result. Let xn be a sequence of random k vectors, that means random vectors of dimension k, such that xn minus a equals to big O p of Rn, and Rn is a sequence of positive numbers that goes to 0 as n goes to infinity. If g is a function from Rk to R such that the derivatives del g del xi are continuous within a neighborhood of a for every I, that means for every component of x, then g of xn is a sequence of vectors, equals to summation j equals to 1 to k del ga del xi into x ni minus ai plus small o p of Rn. And we are just going to give an outline of the proof. Just again use Taylor's expansion for several variables. We know that g of x equals to g of a plus summation I equals to 1 to k del del xi of ga into xi minus ai plus small o of modulus of or x minus a. Now, we define h as 1 by modulus of x minus a into gx minus ga minus summation I equals to 1 to k del del xi of ga into xi minus ai if x not equals to a, and this takes a value 0 if x equals to a. Now, defining this function and using again the results that are related to big O and small o, that means orders in probability, proceeding exactly similarly as in the previous result, we can immediately prove this statement, this result. So, this is very important extension of Taylor's theorem, and this is the extension in case of several variables. That means now whenever we have a random vector, we can easily think of Taylor's expansion. That is, Taylor's expansion is a very important tool in dealing with some theorems or some results or analysis with respect to multivariate observations or random vectors. Now we have some extremely important and important tools in our hand, in the sense that we know Taylor's series expansion in case of real numbers or in case of a real variable from real analysis or calculus. Now we know how to define or develop Taylor's expansion for a random variable. We also know the extension of this Taylor's expansion in case of multivariate random vector. The advantage is that this Taylor series expansion in probability can be used in many areas in developing or proving many important results in statistics, especially in large sample theory. So, we will discuss its advantage or the use of this Taylor's expansion later, but for the moment we should remember that this Taylor series expansion in probability is extremely important, and it is extremely useful in developing or proving many results that are essential in not only in statistics but also in statistical inference. As for example, if we want to test a particular parameter and the test statistics might not have a very compact form, or it is not coming naturally, or the natural test statistic might have a very complicated distribution, Just application of this Taylor series expansion in case of sample, when the sample size is very large, it might be very helpful, and the entire thing will be very easy to handle.